Hi everyone. In this project, I implemented a 2D point class that functions as a small vector geometry library. So the class stores x and y as doubles. I provide constructors, default constructors and parameterized ones. I have construct getters and I also have setters here. I implemented most arithmetic operators as non-member functions, which I can show you in a bit here. So this was to make sure of symmetric operations like point minus scalar, scalar times point, and all that. Addition and subtraction are component-wise, and scalar multiplication scales both coordinates. So for equality, I avoided exact floating point comparisons, and I implemented a tolerance-based helper, which these overloaded functions use internally. So I can show you here. This is what it does. It combines relative and absolute tolerances, and it prevents fragile comparisons of operations like, after operations like rotation and normalization. I implemented both dot and cross products, so I can show you the cross product here, right here, and also the dot here. What they do is they return doubles, and they're useful for things like area uh, computations and orientation tests, and also magnitude checks and projections. I implemented the magnitude method, which is useful for computing the Euclidean length, and also there's the normalize method, which converts a vector to unit length. I also have this rotation, the rotate method, which rotates a point about a pivot, which is by default the origin, and also has the counterclockwise direction by default. But these you can change, and it requires you to pass in your angle in degrees. I can do something about that in the future, but this is basically my class, and thanks for watching.
All right, so this is the box class. The box, it's representing a 2D rectangle, and this is designed to store the center position and then the half dimensions instead of the regular corners. This ensures that collision detection, it's in constant time, that is O of 1. And this is important because we would have many objects that will be moving around. Okay, so from line 50 and beyond, you'll see that this function does three things. So the position is here so that you could set the position using the center or the bottom left. And this makes it clear what to see that you're controlling something. And then there are transformations. The transformations will help us move the boxes, scale the boxes, and also expand the boxes uniformly. And then the third part is the collision. Um, this collision class will check if two boxes are overlapping, if a box and a circle are colliding, or if a point is inside the box. That is, and it will also calculate distances. Okay, so the reason why this class is important is that it will integrate with a few of our other geometry classes. As you can see, we have our point and our circle class here. Um, and also importantly, it will provide functionality for the surface class, like when we want to calculate bounding boxes and then distances. Okay, and then to ensure that this is reliable, there are a few tests that are here that are all passing as at the point of this recording. So I would say that the box class is complete and it's ready to support the simulation um, collision detection needs. Thank you.
I'm Joshua, and I'll be talking about the scheduler class. So the scheduler class allows you to add processes in the class. So if you have agents or different features of your world and you want to schedule who goes next based on priorities. So the scheduler class has two modes. The first one is a deterministic mode, and the second one is probabilistic mode, which I'll be talking about next. So with the deterministic mode, based on the weight of um, the agent or whatever that you're adding, that particular agent will be run more often. So when you look at the code, we define the scheduler as using scheduler with size of t. And mind you, you can pass in any parameter over here. It's a templated class, so it doesn't care what item that you're storing with the scheduler. So when you define this way and you pass in the mode, so this time I'm using deterministic over here, and you add all the processes, so process 1, 2, 3, and you add the weight. So here the weight is 10, 5, and 1. So I want to show you how it works. Let me make. Yep. Okay. So when I run the code, you can see we added 3 processes, just like what I showed you. And the first process had a weight of 10, 5, and 1. And when we call the scheduler.nest, when you go to the code, the scheduler have a method that is called scheduler.nest, and it gives you the next process that needs to be run. So when we call that, you can see process 1 run, and when we check how many times the process run, so we called scheduler.nest for 20 times. When we go to the loop, 16 times. Sorry, we're calling it 16 times. And within those 16 times, we can see we are getting process 1 10 times, and process 2 5 times, and process 3 only 1 time. This is because of the weights, right? And the second mode of the scheduler class is the probabilistic usage. So with the probabilistic usage, we define it the same way. We give it the weight, so we're giving it 10, 5, and 1. And over here, I'm going to call it 10,000 times, right? And we're going to visualize how it's going to be. So okay. So with the probabilistic, running it 1,000 times, you can see process 1 is run 617 times, and process 2 is run 322, and process 3 is 61 times, based on the weights that we pass. So it uses a random generator to get the next item. It's not deterministic compared to the deterministic. And the last thing that I want to talk about is starvation usage. So you see, let's assume if we give one process a weight of 100, as we're using over here, and we give another process a weight of 1, you're going to realize that there's going to be a bias, because the process with a weight of 100 is going to run almost all the time, right? And this process with a weight of 1 is not going to get time to be called. So starvation prevention enables that we are not always calling the same function all the time. So I have an auto adjustment weight over here. So over here, I'm using auto adjustment weight to be false to demonstrate how the scheduler class is going to run if we are not enabling it. And in the second process, I'm going to set it to true. And after setting it to true, we're going to compare how the scheduler class will be behaving if we are adjusting the weight, so as to get fair chance. So I'm going to do make. Okay. Okay, so now let's look at it. When I run the code, so first setup, we have process 1 to be 100 and process 2 to be just 1 weight. And without auto adjustment, when we run it for the first 20 cycle, we have process 1 running 100 times and process 2 running 0 times. So you can see process 2 is being stopped because the process 2 has a weight of just 1. And when we enable auto adjustment for 20 cycles, we can see there's equal distribution. Process 1 is now being called 53 times and process 2 is being called 47 times. So yeah, that is how you use the auto adjustment to adjust the different weights of it. And the process is very simple. You just first reset the dynamic weights, you enable auto adjustment, you set minimum weight, and you set frequency. So the frequency is more like a penalty. The more a process is being called, the more we penalize it. So if you set this to be a very high value, you're going to penalize it with a very strong number. And this is like a weight boost factor, which says that if a process has been in the scheduler for so too long that we have not been called, we should boost that weight. So yeah, that's for the scheduler class. There are different methods in the scheduler.hpp file that you can use, but I'll be talking about these here. Thank you.
Surface class overview. Overall designs and goals. The purpose of the surface class is to provide a spatial manager for 2D shapes, including circle and box objects. It aims to provide overlap detection efficiently and quickly enough with a significant number of objects while being easy to use and maintain. The class allows for detecting all overlaps between objects and more specific checks. The key aspects of the program include the ability to work with both circle and box shapes using sectors to identify overlaps between shapes. The class assigns unique IDs to each shape for fast updating. The internal structure of the program involves entries for each shape consisting of shape type, shaped ID, and occupied cells vector. Sectors use an unordered map with some cell keys shaped list. The program is able to increment next ID values for simple management. The world is partitioned as cells of specified size. Each station is inserted into all shells that overlap with its boundary. Collision checks are restricted to shapes that share sectors, which allow for efficient checking. The overall benefits of this design is that it is simple, has predictable patterns, memory access, and provides easy incremental updates. Many of the key functions implemented by the class include add circle, add box, remove shape, circle, update box, translate shape, query various all shape IDs, and more. Performance. Depending on the size of the sectors, there is a trade-off between objects occupying many cells when it is too small, and more shapes per cell when it is too large. Overall, the surface class is a spatial manager which performs collision detection using sectors and can be efficient for reasonably large size uses.
All right, so this is Limo. I work on the circle class for group 13, and this is an example usage for the circle and how it could be used. Okay, so this circle was made under the namespace ESE498, so it can be used within the context of this class. So in this example usage file, I have various functions demonstrating how you can construct a file. You can construct a circle from using the centers and then the radius. And also we have an example demonstrating the containment. Okay, so how we contain stuff in the circle. to notice boundaries so we don't go over the boundaries we set for the circle or out of the circumference of the circle. And I also have a function demonstrating how we can have overlaps and separations. So when two circles come together and they're overlapping, how do we notice the overlapping? And then if they are not overlapping and they are close to each other, how do we know the distance between them and all that? And also, as you can see here on line 79, I have this function demonstrating the distance. Like I said earlier, when there's a distance between any two circles that are in close proximity, how do we notice that? And then there's a function here that is also demonstrating circle containment, and we also have an example demonstrating circle interactions. When two or more circles are interacting with each other, how do we go, how the code works and all that. So you can see all that here. I like that you all going through the circle and try using it. And then if you find any other functions that you think would be useful for us, for a group or as a company in general, feel free to let me know and then I can implement those functions. Thank you.